Good day, everyone. I am Elbren O. Antonio from the College of Computer Studies at Sultan Kudarat State University. It's an honor to be part of this conference and to share with you my research titled FGSM Attack Impact on MNIST Classifiers via Pytorch Lightning. This work explores how even highly accurate models like convolutional neural networks, often seen as reliable and powerful, can be surprisingly vulnerable to simple adversarial attacks. Specifically, we investigate the fast gradient sign method or FGSM and how it affects classification accuracy using the well-known MNIST dataset. Through this presentation, I hope to highlight the importance of not only building intelligent AI models, but also making them robust and secure against exploitation. Convolutional neural networks, or CNNs, are among the most powerful tools in modern artificial intelligence. What sets them apart is their ability to automatically learn features and patterns directly from raw images data without manual human intervention. This makes them especially effective in tasks when their visual understanding is key. The image on the upper right gives a glimpse of how a CNN works. An image enters the network, then passes through several stages. Convolution layers that detect patterns like edges and textures. Polling layers that reduce dimensionality. And finally, fully connected layers that make decisions based on those features. It's like teaching a computer how to see and understand the world the way we do, but much faster and scale. Now, look at the example below. That a facial recognition application powered by a CNN, it detects the face in real time and assigns a confidence score. Here, 98% sure it's a match. The same technology is widely used in surveillance systems, smartphone authentication, and even emotion detection. Beyond faces, CNNs are also behind handwritten digit recognition, like what used in postal sorting and banking. They're also driving breakthroughs in medical imaging, helping doctors identify diseases from X-rays, MRIs, and CT scans with greater speed and accuracy. So overall, CNNs have revolutionized how machines process images and have become an essential part of many applications we now rely on in our daily lives. Convolutional neural networks have become a go-to solution in many industries because of their impressive performance. Their ability to recognize patterns, detect features, and make prediction with high accuracy has made them an essential part of modern technology. Just take a look at two major areas where CNNs are making a huge impact. First, in the automotive industry, CNNs are the backbone of self-driving cars. These systems rely on real-time image and video analysis to understand the world around them. Detecting lane markings, traffic signs, pedestrians, and other vehicles without CNNs, autonomous vehicles would not be able to interpret visual data fast or accurately enough to make safe driving decisions. In essence, CNN help these cars see and react like human drivers, only faster. Next, consider the field of security. CNNs are now widely used in surveillance systems. to automatically detect unusual activities, recognize faces, or even alert authorities when a potential threat is identified. This system reduces the need for constant human monitoring while improving the speed and reliability of threat detection. The takeaway here is that CNNs are not just theoretical models confined to research. They are real-world tools that are already transforming industries. Their success in applications like self-driving cars and security systems highlight just how important they become. But as we'll see in this research, even these powerful systems are not immune to manipulation and vulnerabilities. At first glance, convolutional neural network seems like the gold standard in AI. They're fast, efficient, and deliver impressively high accuracy, which is why they're used in everything from medical diagnosis to autonomous vehicles. But what many people don't realize is that this accuracy can be misleading. Beneath the surface of their high performance lies a subtle but dangerous vulnerability, one that attackers can exploit without even needing full access to the model. Imagine this. A model confidently identifies a stop sign in a self-driving car scenario. But what with a few tiny, carefully chosen changes? Ones that we can't even detect with the human eye. The model suddenly thinks that stop sign is a speed limit sign. That's how easy it is to fool CNNs. This is where my research begins. We're not questioning the power of CNNs. Instead, we're exposing their weak points. Specifically, we focus on how even a simple method like the FGSM can deceive a model that would otherwise seem perfectly reliable. These vulnerabilities could be the entry points for future cyber attacks, especially in systems where safety and accuracy are critical. That's why understanding and mitigating this risk is not just an academic exercise, it's a necessary step in making AI systems safer and more trustworthy. While CNN are widely celebrated for their high accuracy and efficiency, especially in image recognition, they're not as perfect as the same. In fact, one of the most concerning aspects of convolutional neural network is that with all their power, they can still be easily fooled. The trick lies in what we call adversarial examples. These are inputs that look totally normal to the human eye. No blur, no distortion, no odd colors, but have been subtly altered in a way that mislead the model. Take the image you see on the left, for example. It clearly shows a bird. No human would say otherwise, but when this image is passed through a CNN that has been slightly manipulated, the model confidently labels it as an airliner and with over 98% certainty. This happened because of something called aperture vision, a small, carefully calculated change added to the image pixel values. It's not random noise. It's a strategic tweak that takes advantage of how the model interprets the data. Now, imagine this kind of vulnerability in real-world system. What if a self-driving car misidentifies a stop sign or a security system fails to recognize an intruder? Now that we understand CNNs can be fooled, let's talk about how it actually done. This method used in this study is called the FGSM method. It's simple, fast, and surprisingly effective, which is exactly why it's so concerning. Here how it works. FGSM looks at the model's internal structure and figures which direction would increase the model's loss. In other words, which direction would confuse the model the most. Once that direction is known, FGSM then adjusts its pixels of the image slightly toward that direction. These changes are often so small that the human eye can't even notice them. But for the model, it's enough to cause a completely wrong prediction. If you look at the 3D surface graph on the right, this represents how the model evaluates input. The original start at the bottom, safe and correctly classified. But if GSM takes just one calculated step upward, following the steepest slope in the gradient direction towards the area where the model gets confused. As we can see here, this slide illustrates just how deceptive adversarial attacks can be. On the left, we have two images of a fighter jet. To our human eyes, they look almost identical. No noticeable difference in color, shape, or detail. But to a machine learning model, that tiny difference, what we call perturbation, can be enough to confuse the classifiers. The rightmost image shows a heat map representation of those changes. These are pixel level modification introduced using FGSM, or similar method. They may look artistic or even abstract here, but in reality, they are calculated strategic changes made specifically to manipulate the model prediction. In this part, the image shows that the model prediction for that number is correct, which has a confidence of 99%. But for small perturbation, the model prediction is wrong, but a high confidence of 92%. Let's now take a look closer on this graph, which shows the accuracy of a convolutional neural network over 10 training epochs. The yellow line represents the accuracy on clean and altered data. Then, as you can see, it steadily improves over time, reaching a high of around 95%. This is expected as the model becomes better and recognizing patterns in the training data. However, the orange line tells a different story. This line represents the model accuracy when exposed to adversarial inputs generated using FGSM. Even though the images look the same to us, the small perturbations are enough to confuse the model. The gap between the clean and FGSM lines is consistent, showing that the model performs significantly worse when attacked. By the end of the 10th epoch, while the clean accuracy plateaus at about 95%, the FGSM accuracy dropped to around 85%, a 9% difference. This means that despite the model's excellent performance in normal conditions, its reliability under attack is still concerned. What this tells us in that traditional training alone is not enough to make CNN robust. This graph is visual proof of how simple perturbation can weaken even a well-trained model, emphasizing the importance of adversarial defense strategies in AI. Then let's take a closer look of this loss versus epoch graph. This visual compares how the model performs over time when trained and tested on clean data versus adversarial data generated using FGSM. The yellow line represents the clean loss, That is, how much the model gets wrong when it's fed with standard, unaltered images. As we can see, the yellow lines drop consistently over time, indicating that the model is learning and improving. The lower the loss, the better the model understands the patterns in the data. But now, look at the orange line, which shows the FGSM loss. This is the model performance when adversarial noise is introduced. Notice that this line is always above the yellow line. It decreases as well, but much more slowly, and never reaches the same low values. This means that even though the model is improving on clean data, it continues to struggle when faced with this slightly altered adversarial inputs. So what does this tell us? It highlights a critical weakness. CNNs may appear highly accurate under normal conditions, but they remain vulnerable to minimal, invisible changes. This study has shown that even powerful deep learning models like convolutional neural network are not immune to adversarial attacks. Though, the past gradient sign method, we've demonstrated how small, almost invisible changes can mislead models and reduce the reliability. This highlights an urgent need. As AI continues to advance, so must our focus on security, robustness, and explainability. Defending against adversarial manipulation is not just a technical challenge. It is a critical step toward trustworthy AI. Thank you and good day.